Sure. Okay. Sure. Uh, so running a little bit of okay. So G is multiplied. Okay. And then you have an action to do that. Then you have the job for it. We go to see. Okay. Right. So then you can change some of these assumptions and we can deal with the spring. Yeah. So this spring is effectively. Okay. Now we can use the so here we rolled it. Now we need to pin. Okay. And we see where's the pin? So the spring is right. So the roll right here. Okay. Roll it. Oh, so this is end at the end now. Ah, okay. So now the other is the way we do it. Yeah. This is something that it could, yeah. So if you drop this into ANSYS and theoretically, you bring these two things as separate parts in the assembly, then you would have to define how this connection would be defined or how ANSYS is going to handle it. Okay. So by default, everything defaults to well. We're going to talk about today actually. Oh, okay. So if you have two parts and they're close together, ANSYS is going to assume that they're well mixed together. Okay. That's what's called like a bond. Okay. But you can change that, and so you can change it instead of having the bond there, you can have like a frictionless bond, or you can have like a no separation type of contact as well. Okay. And so that's going to change how those, how many reaction forces go there. With ANSYS, also let's pick up. All right, so let's say we are applying the force. Let's go with that. Yeah. Right. It's going to have a moment, which is going to be creating the force right here. Yep. With ANSYS, because probably what you would have to do, or the way I would do it, I would actually change the CAD geometry so that there would be like an object here. Oh, like a small object. Okay. And then you would apply a force here, and then you can compute the reaction forces on that object as the deformation of the object. Exactly. Yeah. Or you can just compute just the reaction forces. And that'll tell you how much force is that. How much force, I guess in this case, mechanical advantage. Yeah. I brought it up one day. Yeah, you could show. Yeah. No, you definitely could. So maybe you're looking at yeah, sure. Yeah. No, yeah, definitely. I think after today, I think we're going to talk about assembly today. And so we're going to talk a bit. I mean, we're not going to do too much with it today, but just the nature of how two parts are joined together. I think it's just really a lot of freedom. I guess not specifically, but that's something we can probably talk about. Yeah. Okay. Sounds good. So living so right now.
Oh, okay, you're more than it. Okay, just no.
That's not going to look the same.
But I have five.
Also, girl.
Yeah.
Optics. At least on the way back, you can get traffic. Yeah, I guess that's so.
Did you? Super tired of it. Have you looked around? I forgot. Oh.
All right, it's 5:30, so let's go and get started. Good evening, everyone. How's everyone doing today? Good to hear. All right, so today is another ANSYS day, so we have ANSYS activity 3. Our time is going to be kind of a little bit short, but I did remember today that we do have an evacuation. There was another evacuation earlier today at 9:30, and they called / texted me like 5 times. So I definitely got the news of that one, even though I wasn't on campus. We'll probably do the same thing now. Okay, so our next ANSYS activity is a signpost. And so if you go to the Canvas site and you download the specifications for this activity, you'll see the geometry here. Okay. So this is kind of meant, sorry. So this is kind of meant to model a situation where, we have like a freeway signpost over the freeway and it's being subjected to various modes. So, a big signpost like this, a very big structure. I think the most important thing that's the most important consideration is that, it just even supports its own weight. And so we're going to apply its weight, and we're going to apply some forcing due to winds too, which is very, I guess, relevant just because, we just went through a huge windstorm just a couple months ago. And so, we'll see that. Okay. So what's unique about this activity compared to the previous ones, that this is going to be the first time we actually work with an assembly of different parts. So both activity 1 and activity 2, we just had a singular part that we ran the analysis on. This time we're actually going to look at different parts of an assembly and see how they actually connect, and that's going to be part of our discussion. Okay. All right. Any questions I can answer before we get started for today? Okay. All right, and so if you haven't done so already, go ahead and download the specification. Go ahead and download the CAD file. So there are two, so just like activity 2, there are 2 CAD files that I gave you for this activity. We're only going to use the first one for the activity today, and then the second CAD file, the assembly.step, that one you're going to use for your own kind of practice data. Okay. But the one you want to download is solid signpost geometry base.egdb. Okay. So the nice thing about this, this CAD file is that it was actually created within ANSYS itself. So we actually do have some freedom in terms of how we can change the geometry, because that's normally hard to do if you have kind of a solid one. Okay. Okay, so let's go ahead and open up Workbench. Let's go ahead and just do what we usually do. Let's load in static structural. And then let's go ahead and import our part that we just downloaded. So let's right click on geometry, import geometry. And then we're going to look for that solid signpost that we just downloaded. And okay. So before we actually open this up in ANSYS Mechanical, let's go ahead and load in a custom material property. Okay. So if you remember from activity 2, we did this for the first time. So activity 2, we created a new custom material for aluminum. Okay. So we're going to load aluminum in as well here, but we're going to do it in a slightly different way. So if you recall from last time, the way to add a new material property, you need to double click on engineering data. Okay. So double clicking on engineering data, you can see here that we have this one material here, which is structural steel. So let's go ahead and add a second one. Turns out ANSYS actually has a library of different materials that we can actually use. If you do have a very common material. So to open up the library of materials that are within ANSYS, you're going to click on engineering data sources here. And that's going to bring up a new menu. And you can see from the top here that we have different sources for where we can load in the material property. Right? So we have general materials, additive manufacturing materials. We have this ANSYS Grata materials, which I think is just kind of a small sample of their bigger material package. Okay. Composites, explicit hyperlapse materials, magnetic materials, all that good stuff. For us, the material that we're going to be loading in is under general materials. So go ahead and click on general materials here. And then what that's going to do is that it should change your middle window here to a list of all the general materials that ANSYS has stored. Okay. You can see here we have aluminum alloy, we have concrete, copper alloy, FR4, cast iron, magnesium, polyethylene, stainless steel. Right. So the one we want to add here is aluminum alloy. So to add the material, first of all, you can click the material to kind of look at the material properties yourself. Okay. You can see if you compare this to the material properties that we used in activity 2, these are very close, just because most alloys and aluminum have very similar properties. But let's go ahead and just add this one to our project. So go ahead and click on the plus arrow next to aluminum alloy. And what that's going to do is that's going to add this material to your project. Okay. So to check to make sure that you loaded your material properly, so go ahead and click on engineering data sources again. Okay. And you should see 2 materials here. So you should see structural steel and the aluminum alloy. Okay. Any questions on this? Everyone able to load in the aluminum alloy kind of the easy way, I guess? Okay. All right, so let's go ahead and close this. That's all we need to do before mechanical. So let's our geometry is actually all good too. So go ahead and double click on model. So this is going to open up ANSYS Mechanical for us. Right. And really, this podium computer is really slow. Usually it doesn't take this long to open up again. There.
Oh, I have no idea why it's like this. Let me bring this down as we can see the part of this better. Okay. So opening up mechanical, you should see your part loaded in just like okay. Everyone able to open up mechanical? Hopefully you guys are a little bit faster than mine. Okay. All right. So like I mentioned, what's different about this part here is that we have an assembly of different parts. So and you can kind of see based on the geometry here as well. So we have one part here that is going to cover the post. Okay. So the post is that cylindrical object that supports the sign post right there. We have a part for the sign itself. Okay. So the sign itself is a separate part. And you see we actually have a third surface here as well. So this is called WX2 application surface. Okay. You're probably wondering what this is. So if you go back to the problem specification here, you'll see that if you look on the side of the post right here, there's actually a wind force that's being applied on that post, okay? And it's a force that actually goes all the way up the post and part of the sign as well. And so since this is a surface where we need to apply a force that spans two different parts, we've actually created a third kind of surface here, a third part, to allow us to apply a force, okay? So this is a very common tactic, and so a lot of times when you're applying forces to, a finite element simulation, a lot of times the geometry itself is not going to be conducive to applying the force in the exact place that you want. And so oftentimes you have to create some extra surfaces or some extra models in order to apply that force. Okay, and that's what this is about. Okay. But before we get to that, let's assign material properties to each of the parts here. Okay. And so if you remember from activity 2, the way we assign material properties is through this geometry window. So to assign a material property, you're going to click on the part, and then you're going to come down to the bottom left-hand side of the screen, and then you're going to look under the setting for material assignment. So by default, every single part, at least in static structural, is going to be made out of structural steel. Okay. So for this signpost, if you kind of go to the project specifications here, you'll see that the sign is actually made of aluminum and the post is made of structural steel. Okay. Okay, so let's go ahead and add those materials in. So for the sign here, we need to change that material property to aluminum. So let's go ahead and change the material assignment from structural steel to aluminum. Okay. And then for the post is already made out of structural steel, and so we don't actually need to change anything for that. Leave that one. We'll leave that one alone. Okay. Okay. Any questions on this so far? Everyone able to assign the materials here? Okay. Good. Okay. So before we move on to the mesh and the boundary conditions, let's look at this WX2 application surface. Okay. And so if you look at how this is assigned in ANSYS, you'll see that there's a little blue question mark next to that name. Okay. So whenever you see kind of that little blue question mark in ANSYS, usually that means ANSYS wants you to assign something or specify something or do something to that before moving on. Otherwise, in some ways you can say that it's underdefined or under constraint. Okay. And so if you click on this WX2 application surface, you'll see that there is one setting in the bottom left for the thickness of this surface. In fact, it's highlighted yellow, for ANSYS to tell you that you need to specify this before moving. Okay. All right. So this application surface is actually quite unique because it's a type of solid called a shell model, which means that it doesn't have any actual geometric thickness to it. Okay. This application surface here isn't an actual part of the model itself. So there's no piece of duct tape that runs from the top of this post down to the bottom, right? This is kind of almost like a fictitious surface or kind of a ghost surface that we use just for the sake of applying the boundary. And so the way we do that in ANSYS is that we kind of create this extra surface, but we give it kind of an infinitesimally small thickness so that it doesn't actually contribute to the structure at all. Okay. But when you have kind of a shell model like this, you kind of have to manually assign the thickness to the model here. Okay. And so this thickness here is mostly just kind of like a numerical thickness. It's not actually going to extrude in the model itself. And so you need to give it something just in order for ANSYS to be able to solve for a solution. But you shouldn't make it too thick that it actually contributes to the structure itself. Okay. So for this model, I recommend assigning a thickness of 0.01 inches. Okay. Or in other words, 1e minus 2. So that thickness there is kind of sufficiently small so that, again, it's not going to add any structural strength. But, it's thick enough so that, problems don't occur. Because what can happen sometimes that if you assign this thickness to be too thin, so what I've done in the past for this activity is that I've actually assigned it to be 0.001 inches. Okay, so 1e minus 3. What can happen is that if you assign a thickness that's too small, it can actually cause the entire simulation to kind of blow up, for lack of a better term. So, when you have such kind of a paper thin structure and you're applying such heavy forces to it, it may cause the deformation to be very, very large. Okay? So you don't want to assign a thickness that's too small, but you don't want it to be too thick too, so kind of somewhere in between. And so somewhere, even I think even 0.1 inches is fine too. So I think 0.1 inches that's a tenth of an inch. That's really small, especially compared to a signpost that's the size of a freeway sign. But I think kind of a good compromise is 0.01 inch. That should be good for this application. Okay, and so you can see after we've assigned a thickness for this, then we now have a green check mark next to that WX2 application surface. And so we're now ready to kind of move on. All right, any questions on the thickness of that surface? Good. All right, so next thing we're going to talk about is we're going to talk about the connections between the different parts. Okay. And so when you have an assembly of parts like this, it's possible actually for these parts to slide past each other in the ANSYS simulation. Okay. So there's a lot of applications. There's a lot of cases where you're simulating an assembly of different parts, and two parts, may have some kind of, connection where, they can either slide past each other or rotate past each other. And there's a way for ANSYS to actually account for that as well. Okay. So to look at the connection between the parts, you're going to open up this window on the left-hand side called Connections. Okay. And then you're going to open up the next submenu there called Contact. Okay. And you're going to see that ANSYS has already created 3 different contact regions in the geometry cube. Okay. And if you want to examine the contact regions, you can click on them, and you can see the 2 parts that are connected between those contact regions. Okay. And so, for instance, and ANSYS kind of does this a little bit randomly. So your contact region 1 might be different than mine. But my contact region 1 here is a connection between the sign itself. Okay, you can see that's kind of focused here, as well as the WX2 application surface. Okay, so if you want to see which parts are connected by a connection, they kind of show up here. They also kind of show up in this kind of window, in kind of 2 small windows out here. Okay. You see they're highlighted there. So if you go to contact region 2, you can see that this is the connection between the sign and the post. Okay. And so you can see here that we have, this contact region kind of highlighted in red right here. Okay. And then the third contact region is between that WX2 application surface and the post. Okay. Okay. And then if you wanted to see the actual parts kind of in more detail in terms of what's being connected, you can see their names in the bottom left-hand side of the screen as well. So for instance, let's look at contact region 2. That's kind of the easiest one to see. Okay. So if you look at the contact region 2, and you look at kind of the entries that are in red and blue in the bottom left, you can see here that one is the sign, which is a solid body, and the other is a post, which is a solid body as well. Okay. Okay, so whenever you bring in an assembly of parts, and those parts are kind of sufficiently close to each other in the assembly, ANSYS is actually going to create some automatic connection for you, just to kind of define how those parts are going to be. Okay, all right. So those are all the connections, and because all these parts are geometrically very close, ANSYS kind of automatically generated these contacts. So let's talk about how we can modify these contacts. So if you look on the bottom left, there's a setting here for the type of connection for those parts. Okay. And so by default, what ANSYS is going to assume is that if you have an assembly of different parts, any parts that are touching each other in the assembly are going to be bonded to each other. Okay. And so a bonded support is kind of the default. And what that basically assumes is that it assumes that these two parts are kind of, they basically behave as one. So they're kind of, essentially they're welded together or they're bolted together very strongly. So, there's going to be no separation, no sliding, no movement between the parts. Okay. That's the simplest thing to do. The simplest thing is to have a bonded support. Okay. And you can see that for all of the contact regions here that they are all bonded. Okay. But of course you can change this. So if you have an application where you have two parts in assembly where they can either slide past each other or they can separate and move past each other, you can change this type here. So you can go from bonded, right? And so you can change it to no separation. You can change it to frictionless. You can even add a coefficient of friction there. And so let's say that you have two surfaces that are going to slide, but there's some friction between them that's going to prevent that sliding. Then you can actually apply a coefficient of friction, apply either a rough support or a frictional support there as well. Okay. But for now, we're not going to play around with it too much, at least not yet. And so go ahead and leave all the supports as bonded. And then, and later on in the semester, we'll talk more about kind of these things. So a lot of those supports actually, if you change them, they introduce something called a nonlinearity into your simulation, which can add a lot of cost. Okay. All right. Any questions on the contact here? Okay. All right. And so that's the contacts. And so we'll be diving more into that as we kind of do more assemblies. Okay. Well, let's go ahead and actually start simulating. So let's start with the mesh. Okay. So I'll let you guys kind of do the mesh yourself. So I'll give you about 10 minutes to do it. What I want you guys to do for the mesh is I want you to supply a different mesh sizing and a different mesh method for the post and the sign itself. Okay. So in total, you should have 4 different mesh objects down here. So you should have a meshing method, 2 methods. So one for the sign and one for the post. And I want you to create sizing objects for each one as well. Sizing, so this is sign sizing, as well as post sizing. Okay, so I'll give you guys 10 minutes to work on that. And I want you guys to really think about kind of what element shapes, what element order, and what element size to choose for this as well. Okay. Keep in mind that, you want to be kind of a little bit judicious in terms of how you allocate the elements in this mesh. Because this is such a large model, it's the number of elements in this model can blow up very easily. And so you want to make sure that you're a little bit kind of strategic in terms of where you put the mesh in. Okay. In particular, I want you guys to think about based on the loading for this model up here. Okay. So essentially, we are going to have a lot of bending stresses here. So we have the weight of gravity as well as the wind forces. Okay. Think about what part of the signpost is going to be experiencing the most structural stress. Okay. So think back to activity 2. Think back to what parts of that bike crank experience the most stress in terms of the forces applied. And I want you to use that criteria to kind of refine the mesh in those areas. Okay. Whereas the areas where you think are not going to experience a lot of stress, maybe you put a force mesh there too. Okay. And also feel free if you want to add some additional sizing objects or you want to add refinement, you can do that as well. But at the very least, you should have these 4 meshing objects here. So a method for the sign, a sizing for the sign, a method for the post, and a sizing for the post as well. Okay. All right, so I'll let you guys work on that until about 6 o'clock, and then if you have questions, just raise your hand, and I'll come around to you.
Just one.
Transfer interest is you cannot run that. 1,000.
Yeah. Wait, what? Just kidding.
How's everyone doing? Any questions? So,
Well,
She's
just,
just a tweet.
okay. All right, so it kind of seems like everyone's kind of on board, and so, we do have to end early today, so I'm gonna cut this off a bit early. But this is kind of what I have for my mesh, and so kind of just based on what I know about the simulation, I know that this post is gonna be the one that's gonna be doing most of the support for this sign post here. And so it makes sense that the post here is going to have the most structural stress. The post is essentially gonna be the one that's supporting this whole thing. And so my strategy with the mesh is because I know that the stresses inside the post are going to be much higher than the sign itself. I use a much finer mesh within the signpost. And then the sign itself, I used a fairly coarse mesh. Okay. So that was kind of my strategy here. And so for both ones, I used the hex dominant, even for the curved post here, just because, you know, if ANSYS can do it, great. If not, then that's okay. But, you know, you can see here that ANSYS actually did a pretty good job filling this mesh here with a bunch of hexadecision. Okay. All right, any questions on the meshing? Okay, all right, so let's go ahead and move on to the boundary conditions, if you haven't already. Okay, so for the boundary conditions, we actually have quite a few boundary conditions to apply here. If we go back to the specifications here, you can see here that we have to apply the weight of the sign and the post itself, okay? And there are a couple wind forces that we're going to apply as well. So we're going to apply a wind force that's kind of hitting the sign perpendicular to it. And then of course we have the spatially varying force that's going to be applied on the left-hand side of the sign itself. Okay. Okay, so let's start with the gravity forces. And so actually there's a very easy way in ANSYS to apply gravity forces like this. And so if you look back at the document, you know, it looks like the gravity forces are actually applied as separate forces here. You don't need to do that in ANSYS actually. So there's a very easy way to do that. And so there's a special boundary condition that you can add. So if you right click on static structural A5, you go to insert, you'll see that there is a special condition here called standard earth gravity. And so what that's going to do is that it's going to apply a weight force to all of your parts that is proportional to, you know, the weight of the object itself. And the way it does this is that it computes the weight of the object based on the density of the object, as well as the acceleration due to gravity and the volume. Okay. So this is kind of a very easy way if you think that weight is going to be a significant factor in your simulation, which in this case it is because we have such a massive part here. There's a lot of weight that this post needs to support. Okay, and you can just add standard Earth gravity, and that's kind of a very easy way to do it. All right, so the next force that we're going to add here is the perpendicular force on the sign itself. Okay. And so this force is actually quite unique because this force, the way that we're going to apply it is we're going to apply this as a point force. Okay. Okay. So to apply a point force, let's go ahead and right click on static structural A5. Let's go to insert. Let's go to force here. Okay. And we want to apply this force onto a small point on the sign itself. Okay. Now, it's very hard to see. In fact, you know, I think it's impossible to see. And so if you're having trouble finding that small point on the middle there, go ahead and switch the selection mode in ANSYS to vertex, or you can hit Control P, okay? And then you're going to kind of like mouse around kind of the middle of the sign a little bit. And there's going to be one point in the middle there which kind of highlights gray when you mouse over. Okay. So it's really kind of hard to see there. Yeah, so if you kind of mouse, you kind of should be a little bit careful right in the middle. There's a small point right there which will highlight gray when you mouse over it. Can you go ahead and mouse over that? It's harder and harder every year as the arthritis creeps in. I think I clicked it. So after you click it, go ahead and hit apply. Okay, I missed it. All right, it's not today.
So when it shows that sign on the new cursor, you can actually click it.
Oh yeah. Oh really?
Yeah.
It's in there somewhere. Oh, there it is. Okay, thank you. There it is. Okay. All right, so that is our wind force. Now, normally you don't want to do this. Like we mentioned kind of before when we talked about boundary conditions, normally you want to apply your force onto as wide of a surface as possible. And that's especially true for this case, because this force here represents the force of wind that's being applied onto your sign. So ideally, you would want to apply it onto this entire surface here. But, you know, I did kind of want to show you that you can apply forces on a point. It's just that most of the time, this is usually not ideal, okay? Okay, so with that point selected, let's go ahead and apply the force here. So just like we normally do, let's change the definition of this force to components. Okay. And then let's go ahead and apply a force in the y direction with a magnitude of 8,000. Okay, good. All right, and if you're having trouble finding that, don't worry, it took me an embarrassingly large amount of time to find that point too. So it's hard, and that's why normally you don't want to do it. Okay, any questions on standard Earth gravity or just that point force there? Okay. All right, so next thing we want to add here is we want to add this varying force on the axis of the post. Okay. And so this is where that WX2 application surface is going to come. Okay. All right, so let's go ahead and add, we're actually going to add this as a pressure force. So let's go ahead and right click on static structural A5. We're going to add pressure. And then for the application surface, we're going to click on that small strip that's going up and down. Okay, if you want to click on that WX2 application surface, go ahead and hit apply. Okay. And we're actually going to apply a force here that's going to be varied. Okay. So, for all the forces that we've applied up to this point, we've assumed kind of a constant force or a uniform force. This one, the magnitude of the force is going to change based on the z direction. So if you go back to the figure here, you can see that we have kind of a triangle wave here. We have kind of very small amount of force at the bottom, but then this force kind of ramps up as you get higher and higher. Okay. So to add a spatially varying force, you basically are going to apply a function or an Excel function within ANSYS itself. Okay. Okay. So the way to apply this is to apply a function is to add an equal sign. You're going to see inside this window that says magnitude, you're going to go to tools. Okay. And the function that we're going to apply here is 0.1 multiplied by z, where z is the kind of the z coordinate of this structure. Okay, and so if you do that and you hit enter, you can see here that it's showing us the kind of variation of force. And so the force should start at a magnitude of about 0 at the bottom because the bottom of the signpost is at the origin. And it should come up to a maximum value of about 43.2 psi, about 43.1999. Okay. Was everyone able to add that spatially varying force onto the post? Okay, good. And for this one, you want to be careful of the units too, because it's assuming that all this is in PSI. And so if your units are not in PSI, go ahead and change that there. All right, so the last thing we need to do before we run the simulation is we need to fix the force. So let's go ahead and add that. So let's right click on static structural A5, go to fix the force. And let's apply that on the bottom of the sign itself. Okay, so that's where the signpost is going to be fixed to the ground. And then let's go ahead and run a simulation. So for our solution here, let's go ahead and add some results. Let's add total deformation like we usually do. Let's add equivalent stress like we usually do. Okay. For this one too, let's also add some normal stresses as well. So let's go ahead and add normal stress, because we're going to want to see how much this signpost is being compressed or tense. Okay. And then let's go ahead and run the simulation. Go ahead and click solve. Okay. These results here. Okay. Okay, so this is actually interesting. Okay, so first thing you want to look at in this case is the total deformation results. Okay. And one thing you should look out for is, usually the way that ANSYS kind of scales these color bars here is that whatever is the maximum amount of deformation, that's going to show up kind of bright red. Okay. But if you notice here, there's no part of the model that immediately jumps out as bright red. Okay. And the reason for that kind of has to do with our application surface that we kind of discussed earlier. And so it turns out that the application surface that we applied here is actually too thin with 1 times E minus 2 inches. Okay. Because what I'm seeing here is that, ideally what should happen is that the tip of this sign here should be at maximum deformation. But I think what's happening is that, this application surface is so thin that it's actually not reaching there. So if you're curious about where the maximum deformation is, you can go ahead and click on this and then click on result. Okay. And then if you want to see where the maximum deformation is, there's kind of a tag that you can do here as well. So under result, under ANSYS, under ANSYS mechanical, you click on maximum. Okay. And then after you click on maximum here, it's going to show you kind of where the maximum deformation is taking place. Okay. And so according to this figure here, the maximum deformation is actually taking place down here on this kind of little strip that's kind of pulsing through right there. So it looks a little bit kind of misleading, but this little part here actually comes from the application surface that's actually clipping through the model itself. So it shouldn't be doing this. So it shouldn't be clipping in. So let's go and fix it. So let's go back to our WX2 application surface. And let's change the thickness. So instead of 0.01 inches, let's change it to 0.1 inches. So we're going to increase its thickness by a factor of 10. And so that's going to give it a little bit more beef. And so, just so that it doesn't kind of clip through like that. And so this should kind of fix our results. Let's go ahead and solve one more time. That maximum tool that I kind of show you is actually pretty useful, especially when you're looking at stresses in your model. Okay, so let's look at the deformation. Now this looks much better. Okay. You can see here that the maximum deformation is at the tip of the sign, which is about 9 inches, so which is what you should get. Okay. And you can see that the WX2 application surface is kind of taped onto the model as it should be. And of course, you can look at the equivalent stress as well. Okay. All right, you can see here the maximum stress occurs kind of near the bottom of the signpost. Okay. That makes sense because that's the part of the signpost that's kind of supporting all the weight. It's supporting all of the forces, and so it makes sense that that's where the forces are. That's where the stresses are maximum. Generally speaking, you're going to get maximum stresses near the fixed supports in your model. Okay. That makes sense. Now let's look at the normal stresses here. So for the normal stresses, normal stress is direction. So you're going to have to choose which direction the normal stresses are occurring. Okay. Right now, this normal stress that we're looking at is actually in the X direction. So that's looking at the normal stresses in this direction here. But actually, the direction that's going to have the maximum normal stress is actually going to be in the Z direction. So let's go ahead and change it to Z. You may have to rerun the simulation again. And so when you change the normal forces to the Z direction, you can see here that the maximum force is right at the edge of that post, magnitude of 29,605 PSI. All right, was everyone able to get these results here? Question, yes.
I'm getting a bunch of errors. I'm not sure.
Okay, let me come around and I'll come around in a second. Okay, so for those of you who kind of already got this part, I'll let you guys work on the rest of the activity from here. So we've done basically the first 4 problems together in the activity. So problem 1, problem 2, 3, and 4. Okay, so problem 5 of this activity, I want you guys to redesign the post. Okay, because it turns out the stresses that we obtain in this post is way too high. And so the material, this material that we have that comprises our post has a yield strength of 25,000 psi for normal stress. Okay, you can see here from the results that our stresses here are 29,600 psi. So we need to redesign the post, and so without changing the boundary conditions. So don't change the weights, don't change the wind forces. I want you to make a change in the geometry that's going to lessen that stress. Okay. So some ideas that you can think of is that you can change the thickness of the sign, and so that's going to affect how much weight the sign is made out of. You can change the diameter of the post. Okay. You can change the material of the sign as well, or anything else that you want as well. Right. So if you're going to change the geometry, you do have to do that in Design Modeler. So just like in Activity 1, you would have to close out a mechanical, open up this geometry in Design Modeler and change it there. Okay. But I want you to make a change in the post so that the stress is less. Okay. Ideally, it should be less than 25,000. But there's also some limitations here too. Like you can't change the overall height and the overall width of this thing, so it has to be 36 feet high and 13 feet wide. But anything else you can change. Okay. Problem 6 of this activity is I want you to consider 2 different loading scenarios. Okay. And so right now, we've simulated this part under what I call one scenario, one condition, which is essentially just weight of the sign as well as some wind. Okay. I want you to come up with 2 other loading scenarios, so 2 other types of forces or 2 other situations under which you can apply forces onto this signpost and run the simulation for that. Okay. And so for your other situations, you don't have to include the wind forces, and so you can disable these 2 forces here. Okay, that's totally fine. All I want is just 2 unique scenarios or 2 unique combinations of boundary conditions for this sign. Okay. So some ideas is maybe you're gonna look at a situation where a really fat bird like maybe perches on the side of the signpost, and you want to see how that's going to affect the stresses in your signpost. Okay. Another situation you can think of is maybe a car hits or maybe an object strikes the signpost on the side, and you want to see if the signpost is going to survive that. Okay. But I want you to think of 2 different loading scenarios, run the simulations on those, and then report on those results. Okay, so that's problem 6. And then problem 7 is just very similar, just summarize the results. So writing kind of that 1-page memo, that 1-page kind of report on summarize everything that you would send to your boss. And then problem 8 is going to be the finite element analysis on the other CAD model, which is a chair. Okay, so besides the people that need to come around and look at the areas, are there just any questions on just the activity in general? Okay, all right, so you guys have about 15 more minutes until we're forced to evacuate, and so you guys can work on until then. If you have questions, just raise your hand. I'll come around and talk to you guys, but yeah, go ahead and work on it.
That's so much.
Okay, so you need to have a big support. So right now you're applying forces, but there's nothing holding it down. So go ahead and click on static structure 5. Insert a big support. Yep. And then you want to fix it on the bottom. Perfect. Sounds good. Yeah. So most of the stress is going to come straight down. I see this normal stress is in the Z direction. You have to change it from X axis to Z. Yep. Yep. Exactly. Yep. Yep.
20,000.
Yeah.
But it has to be around
Yeah, so FE1 here, that's actually the weight of it. So in this original diagram, that's we applied as kind of an external force applied right on the interface. But actually that standard gravity takes care of both of them. gonna be the weight of bonus. And then, yeah. So the C election.
Why did you see all the extras for the normal strip? If you have the small office, that-
Oh,
Yeah. Pushing. I think- I think that's a lot of time to be there.
Oh, this is a custom. Okay, so I would double check the business. So it's first thing of mine. Those factors are.
You think it's stickless?
Should have been. So I think,
Yeah, but.
yeah.
Especially the younger one.
Now,
It's better than not, no.
thank you.
You don't know how. Like right there, it's also instead that you can dance.
That's. Well, I mean, the max is in the right place. It could just be that your mesh up here.
Oh. Final.
Okay. I think it's because, so right now with your W application service.
Yeah.
So in that case, you know, a 10-inch thing is basically. So it's almost like you're adding kind of a steel bar. 10 inches thick all the way down. That's actually, so this is kind of the other thing. Your application services so thick, it's actually adding structural strength to your. Right, so you need the CPU glass. Actually, honestly, I changed it to 0. I might have said 110. I might have put that quickly. Okay, there. Yeah. So with these kind of modifications, it's a delicate balance, because if you make it too small, so if you make it 0.01, then it actually becomes too flimsy. And it just becomes a whole kind of exactly. You don't want to make it too thick, otherwise then it adds strength. Thank you. Yep. Everyone on Zoom, you guys doing okay? Any questions from the Zoom crowd? I think my volume might have, so if someone was talking just now, I might have, everything's okay for you guys on Zoom?
No. It feels so long. I'm gonna take that. Saturday.
Like that's the shit. They do just one row.
You guys, do it again.
I'm not gonna put the ring on it. Come on.
For everyone, we are evacuating at 6:30, so just take that into account. Make sure you guys save your work and send it home if you. They're gonna let us back in the building afterwards, but just if you want to be safe, in case something happens, like they cut off the power or something like that, just make sure all your work is safe. Yes, so the way to save it is you put a file, say that first. But then I think you're like, yeah. Okay, go ahead, answer that.
I like saw you talking for your first one for a long time, and I was like, oh my god, you did it well. Like, talking, and I thought, no one's talking about it.
Usually want to talk to her.
I don't. Nervous, I needed to like, like, but I saw you talking to him for a long time.
Yeah, it's just like, there's a lot of they're taking away blank where they were not, but all their
Oh,
like,
yeah.
like, this was one company in the middle at the end.
Yeah,
I went up wrong. If I find it, like, yeah, but yeah, so like, yeah, they feel the black life experience, like,
Yeah.
I looked at also like undergrad and grad.
Yeah.
And just went straight to like, oh, sorry, I feel like you.
I feel the same. It's so hard. And then by the last person, it was for like some automotive or something. And I literally, I get huge because I feel a little more girl. So I go out tonight. I have my like, what is it called? Your.
Oh, you practice it? I have not.
I have it, but like after.
So good. Yeah.
Software guy now. So, and she was like.
Yeah, like, I went. Saw that, I mean, yes, we're not very. I didn't say a word to you, though, I was like.
Yeah.
Damn. Gee.
I, by the end of it, I'm hungry.
Yeah.
Okay.
I'll start. The first one was, I don't know if you. Oh, really?
Yeah.
First one, sorry.
And my,
I got an interview for the first one. Should have never got that. So I thought I was in a meeting.
Oh.
And everything, they said it was for like. So, you can assume that the question they're gonna be super like. Hard.
Yeah.
But one of the questions they asked, like, okay, so like. So what is super elevation?
I don't even know what's in
And like, why is it important? And how would it- I've never worked in highway design, like.
I used to have to do with the stress.
I looked it up, and it's one, and so like, I'm trying to.
You would have very.
But after, it's not,
You're like-
it's done, when one will come by, and it's like, why your off ramps are at an angle. So like, so they can fly out.
Yeah.
That's what it is, like, except for.
Nice, have a nice weekend.
Okay, because I.
Do this,
but I
good one.
didn't know that. I didn't know the word, but I knew what wire ramps were sideways. And when there's turns, it's always. Well, yeah, because it wouldn't imagine a curve, it's straight. Oh.
I got an idea for the city, just to be.
no, that's all right. Because they asked it probably.
Yeah.
Already a little bit better.
I think another question they asked me towards the end was like, if you were to put an end. That's people like information, right, there's still like how we. Analyze what is sensitive, and like how we make sure that you're on it, what you're on. Oh. Well, this is a new brand.
Yeah.
What?
I didn't call it, I didn't get a call back from you to say.
Okay.
But at least now you know what they might look for. Yeah,
Yeah, I guess like that. It was pretty,
intimidating.
intimidating.
Oh my god.
That's crazy. Now I'm scared.
I know, it's good too. Thank you.
Thank you. Have a good night.
Have a good weekend, guys. You got any final questions? I do have to sign off because we have to evacuate in the room. Question again. I said 45.
Thank you, Doc. See you, Doctor.
You guys have a good weekend.
I just studied everything, like.